chemistry friends. We're here today to talk about the kinetic molecular theory. We're in the gas law unit, and I'm looking at packet page 1 right now. So you might want to go grab your packet, turn it to page 1 if you don't already have it. And the kinetic molecular theory, as it states in this first statement here, is it is used to explain why gases behave the way they do. Why gases behave the way they do. You know, there's a few things about gases that I want to make sure that you sort of have an understanding of. I'm going to go ahead and jot just a couple things down over on the side over here. First thing about gases, probably know this already, but again, let's just get it down in your notes anyway. Gases are always in constant random motion. Again, they're moving around inside of whatever kind of container they're in, or moving around in our atmosphere, our oxygen and our nitrogen, things in our atmosphere, constantly and in a random motion. And the speed at which they're moving is a direct relationship to their temperature. We learned about that in our thermodynamics unit. You'll recall that the definition of temperature was defined as the average kinetic energy of the particles. So let's get that down here as well, that the average kinetic energy of our gas particles directly related to the temperature. Now, something else about our gas particles, again, be thinking of them in constant random motion. If they're moving very fast, we know they have a higher temperature. If they're moving slowly, they have a lower temperature. As they're moving about and they're colliding with each other, colliding with the interior of the container, it's the collisions with the interior of the container that they're in, meaning the aerosol can that they're trapped in, or potentially maybe the balloon that they're trapped in. It's the collisions with the interior of the container which causes the pressure. So the collisions of the molecules with the interior of the container is what causes gas pressure. And then just one other thing I want you to know is that we're just going to assume that, again, these gas molecules are spread so far apart one from another, that's what a definition of a gas is, that they're not actually attracted to each other at all. They're too far apart to even be close enough to be attracted. So there are no intermolecular forces of attraction between any of our gas molecules. Okay, so just kind of background a little bit about that. So the kinetic molecular theory, again, explains why gases behave the way that they do. And there's actually 7 different variables that we need to be concerned about when we talk about the behavior of a gas. And you'll notice right here that we have all 7 of these variables mentioned right here. And the first one has to do with the container type. What type of container are our gases in? Okay, if the container is an open container, it's a container in which the gas molecules are free to move in and out as they're in their random motion. On the other hand, a closed container means those gas molecules are trapped. They can't come into the container and they cannot escape from the container. The other thing that we need to be concerned about when we're talking about the behavior of gases is what type of container they're in terms of, is that container flexible, meaning the volume can change, or is the container inflexible, meaning the volume is constant? So again, when we're talking about the flexibility of the container, we're looking at the volume. If the volume is constant, meaning it does not change, then we've got ourselves an inflexible container. Like an aerosol can. The volume doesn't change on that. That's an inflexible container. Whereas a flexible container, you might think of a balloon as being flexible. You know that a balloon can increase in size or decrease in size. Flexible container. The other thing that affects the way gases behave is, well, how much of the gas do you actually have? We're in chemistry, so when we're talking about how much gas we have, we'll be referring to the number of moles of gas. Please note that our moles of gas are going to be represented by the variable n. Now, we just referred to the fact that we're going to be talking about the temperature and the kinetic energy and how they're directly related to each other. The thing about temperature is the temperature is only going to change if we change it. So in other words, we take a sample of gas and we put it on ice. We're decreasing the temperature. or we have a sample of gas that's in a container that we put on a hot plate, we're increasing the temperature. So again, temperature only changes if we change it. And then the other things that we've mentioned, we're going to be referring to the collisions that are occurring on the inside of the container, and we're referring to then the resulting pressure as well as the volume of the container. Now, some relationships that exist between these variables. Mentioned them already, but we've got them listed here as well. Remember, it's the collisions with the interior of the container that are causing the pressure. And the temperature and the kinetic energy, when we say, I've said this a few times, that they're directly related, when we're talking about something being directly related, we mean that as one goes up, the other goes up. So if we have an increase of temperature, we're also going to have an increase of kinetic energy. Conversely, if the temperature goes down, we'll have a decrease in the kinetic energy. Now what we're going to do is we're going to get talking a little bit more about these collisions, and this is where it might start getting a little bit more complicated. Because when you have the number of collisions on the inside of your container changing, different things are going to happen depending on the type of container that you're in. If the container is flexible versus if the container is inflexible. So the first thing we're going to be talking about is, let's say we're in a container that is inflexible. Again, let's be thinking about, say, an aerosol can where the container is inflexible. And if for whatever reason we cause the number of collisions to go up, now if you have more collisions inside of that inflexible container, you are going to have more pressure. Your volume is staying constant, your temperature and kinetic energy are constant, and your number of moles are constant. Your increase of collisions will cause an increase of pressure. Again, if it's an inflexible container. But what if we've got ourselves a flexible container, like a balloon, and for whatever reason we have an increased number of collisions? Well, again, you might be thinking that the increase of collisions will cause an increase of pressure, but you know what? This is only momentary. Why is it only momentary? Because if you have an increased amount of collisions, meaning an increased amount of pressure in a flexible container, those increased collisions are actually going to cause your volume to go up. More collisions will make that volume go up. Now, the volume is going to go up until the pressure on the inside of the container is equivalent to the pressure on the outside of the container. Wait a minute, what's this pressure on the outside of the container? Well, remember our atmosphere that has our oxygen molecules, our nitrogen molecules that are constant random motion, they're hitting the outside of the balloon. So our balloon is going to increase in size until, again, the pressure on the inside equals the pressure on the outside. And then our other variables are remaining constant. The other thing to think about is that we've got an open container. If we do have an open container, molecules are free to move in and out. Therefore, our number of moles can change. So if we're talking about a flexible container, remember, the definition of a flexible container is that its volume can change. An inflexible container is where the volume cannot change or remain constant. So a balloon. Can a balloon's volume change? Absolutely. So a balloon is going to be considered a flexible container. What about an aerosol can? Again, an aerosol can, the container is pretty inflexible there. Volume can't change, so we've got an inflexible container. A syringe. Think about a syringe where, not where you're going to put a liquid sample in, say like you might think of a syringe where you're going to get a shot from the doctor. Let's think about a syringe where we're going to actually put a gas sample. Let's see if I can draw a picture of a syringe. So there we've got the body of the syringe, and then this is the plunger. And remember, the plunger can move in or out. If I push that plunger in, I'm decreasing the sample size. If I'm pulling the pressure out, or the plunger out, I'm increasing the sample size, the volume size. So believe it or not, this is considered a flexible container if I allow that plunger to move freely in and out. The syringe itself is made of an inflexible material, but the plunger moves in and out. That's why it's flexible. All right, so these 7 variables, You better start memorizing what the 7 different variables are, because if you need to use all 7 of them to explain the behavior of a gas, then you need to make sure you have all 7 memorized. So we're adding more molecules to the same amount of space. This is an example. So I've got myself an aerosol can with a certain amount of gas in it. Here is the initial situation. And again, what my change is going to be is I'm going to add more molecules. You can see this in the picture right here. I have a few number of molecules in the top can, and I have a lot more in the bottom can. So, which variable did I cause to change? Well, I added more molecules. More molecules means that I'm increasing the number of moles of gas. Notice I'm not writing this out in sentences. You can if you want. I'm going to use a little shorthand by using an arrow up indicating increase, N meaning the number of moles. If I have an increase in the number of moles of gas, guess what? I'm going to have an increase in number of collisions. Well, if you've got an increase in number of collisions, remember different things happens depending on the container type. So you must, when you're mentioning a change in collisions, you must then mention the container type. I have increased number of collisions, and I have this in a closed, inflexible container. And what we mentioned up above is if we have increased number of collisions in a closed, inflexible container, we're going to have an increase of pressure. Okay, so when you think about it, you add more gas molecules to an aerosol can, the pressure is going to go up. No, that's not what I want to know. I want to know, using the 7 variables of the KMT, why the pressure goes up. Because if you increase the number of moles, you increase collisions, and increasing collisions in a closed, inflexible container causes an increase of pressure. You know, I only mentioned 4 variables. There's 3 variables I didn't mention. I didn't mention them yet because they remain constant, but they have to be mentioned that they do remain constant. The temperature didn't change, therefore the kinetic energy didn't change, and the volume didn't change either. So now, here I have my 7 variables of the kinetic molecular theory mentioned, explaining why adding more molecules of gas to a aerosol can increases the pressure. Let's try another one. Let's say I increase the temperature of a sample of gas. So this is my initial condition, and my change here is that I've increased the temperature. The longer arrow is indicating that. So what I've done is I've increased the temperature. Again, directly related to the temperature is the kinetic energy. If I increase the temperature, I increase the kinetic energy. If they're moving more quickly, ladies and gentlemen, they are going to be colliding with the interior of the container more frequently. So I've got an increased number of collisions. We just said this. When we talk about increased number of collisions, we need to know about the container type. According to this information I have in my picture, that volume didn't change. So I have, and you notice that it's a full box, so I again have a closed, inflexible container. And what we said before is if you have a closed, inflexible container with increased collisions, you will have an increased pressure. 1, 2, 3, 4. I've mentioned 5 of my variables. There must be a couple variables then that remain constant. The things that remain constant, that didn't change in this case, I didn't change the number of gas molecules, so the number of moles remains constant, and also I did not change the volume. That remains constant. Let's do one more example together. Let's say I decrease the volume. Notice I decrease the volume by pushing that plunger down. So if I decrease the volume, you know what? Those molecules are trapped in a smaller space, so that's going to increase the number of collisions. Now, when we talk about collisions, remember we need to talk about container type. This is obviously a closed container. Now, I'm going to hold that plunger in place, and I'm going to hold it in place so it is an inflexible container. And again, this is the 3rd time in a row where we have increased collisions in a closed, inflexible container causes an increase in pressure. What didn't we change? What remained constant? Oh, my time's up. What remained constant is the volume remained constant and the number of moles remained I'm sorry, the volume didn't remain constant. I'm going to have to change that there. That timer bothered me there. What remains constant is the number of moles remains constant, the temperature remains constant, and the kinetic energy remained constant. 1, 2, 3, 4, 5, 6, 7. We're done with our notes.